Welcome. Today we're diving deep into the world of AI and Java, step by step, stage by stage. We'll explore key concepts like large language models, vector search, and Spring AI, all through the lens of real, production-ready Spring Boot code. This is the #1 AI question every Java developer faces in 2026 interviews, explained from start to finish. Let's get started. Let's dive into Retrieval-Augmented Generation, or RAG, in Java. This approach works with any chat model, OpenAI, Anthropic, Llama, you name it. The key: it's provider-agnostic and doesn't require fine-tuning the model itself. Instead, we update the knowledge base. RAG combines a search step with a generation step. Before the model answers, it first finds the most relevant info from your private data, like docs, tickets, or wikis, and then generates a response grounded in that data. It's a powerful way to get accurate, context-rich answers. Let's talk about why Retrieval-Augmented Generation, or RAG, is the go-to solution when we want a language model to work with our own data. Instead of fine-tuning the model every time something changes, which gets expensive and slow, RAG lets us just reindex the updated documents. It searches our knowledge base directly, so it can point to exact sources and stay current. Without RAG, models rely on frozen knowledge and can confidently make things up when unsure. RAG fixes those limits, grounding answers in real facts. Let's talk about Retrieval-Augmented Generation, or RAG, in Java. RAG doesn't make the model smarter. Instead, it gives the model the right page to read before answering. Think of it like an open book exam. The model can actually look up the information it needs, then respond based on what's written there. Without RAG, the model answers purely from memory, like a closed book exam. If it never learned a fact or forgot it, it just guesses, confidently, and often it's wrong. Let's dive into the core ideas behind Retrieval-Augmented Generation, or RAG. It all starts with embeddings, turning text into vectors, numbers that capture meaning, not just keywords. Then, semantic similarity: vectors close together mean similar ideas, even if the words differ. Next, vector search, finding those nearest vectors quickly using smart index structures like HNSW, instead of scanning everything. Finally, context augmentation, inserting retrieved text into the prompt so the model generates answers grounded in real information, not guesswork. These 4 concepts power RAG under the hood. Let's walk through what actually happens behind the scenes with Retrieval-Augmented Generation in Java. It all starts offline, with ingestion loading documents like PDFs, tickets, and source files. These get broken into chunks of 500 to 1,000 tokens, with some overlap to keep context. Each chunk is then embedded using the same model we'll use later and stored in a vector database. When a query comes in, it's embedded too, and we use nearest neighbor search to find the most relevant chunks. Those chunks get inserted into a prompt template, helping the language model generate a precise answer based on real context. Let's dive into the architecture behind Retrieval-Augmented Generation in Java. Here, we see 2 main flows. The solid path represents live requests, where queries hit the system in real time. Along the bottom, there's an asynchronous ingestion pipeline. This keeps the VectorStore fresh by continuously chunking and embedding documents, wikis, and tickets. These knowledge sources feed into the VectorStore, powered by tools like pgvector or Pinecone. Then, the language model provider, OpenAI or Anthropic, handles the generation. All of this is wrapped in a Spring Boot API, ready to serve web and mobile clients efficiently. Let's dive into the first topic, Retrieval-Augmented Generation, or RAG, in Java. Here, you'll work with 3 core interfaces. ChatClient handles the conversation flow, letting you send a question and get a response. EmbeddingModel transforms text into vectors, numerical representations that capture meaning. VectorStore stores these vectors and lets you search for similar content quickly. All of this is part of the Spring AI Starter library, which you include in your project's dependencies to get started. Now, let's dive into our first hands-on topic, Retrieval-Augmented Generation, or RAG, implemented in Java. Here, we see a simple controller that handles questions by searching a vector store for the most relevant documents. It then combines those documents into context and passes that to a chat client, which generates an answer strictly based on that context. This minimal example shows the core flow: retrieving, augmenting, and generating, all in just a few lines of code. Now, let's dive into how Retrieval-Augmented Generation, or RAG, looks in Java. This snippet shows a service class designed for production use. It handles tenant isolation by filtering queries, ensuring each tenant only accesses their own data. The service searches for the most relevant documents, then uses them to craft a precise response. Notice the fallback for empty results and the circuit breaker pattern for resilience. This is how we harden RAG for real-world, production-ready applications. When working with Retrieval-Augmented Generation in Java, it's crucial to keep your chunks self-contained. Each one should make sense on its own, without relying on the previous paragraph. Think of chunks like code. Review them carefully, test thoroughly, and be ready to roll back if needed. Version your prompt templates to stay organized. Remember, a wrong answer usually points to a retrieval issue, not the model itself. So, evaluate your retrieval process, not just the final answers. Store rich metadata like source, date, and permissions to enable better filtering later. Overlap chunks by 10 to 15% to avoid cutting ideas in half. And don't mix embedding models between ingestion and query. Pin one model from day one to keep retrieval solid. Let's dive into keeping Retrieval-Augmented Generation fast and smooth in Java. We want users to see tokens streaming in real time, no waiting around for the full response. That means using SSE or Webflux to stream results as they're generated. We never block requests during reindexing, and ingestion happens asynchronously. More chunks don't always mean better answers often. They just add noise and slow things down. So tune your top K retrieval carefully, cache frequent queries, and use an approximate nearest neighbor index like HNSW or IVF once you're past a few thousand vectors. Batch your embeddings and make one API call for many chunks instead of many calls. This approach keeps RAG fast at scale. When working with Retrieval-Augmented Generation in Java, we need to treat everything that comes back from the VectorStore as untrusted input, just like any user input. We can't let retrieved content directly trigger tool calls without validation. Otherwise, sensitive data might slip in unnoticed, including personal information. Without proper filters, one customer's query could accidentally pull up another's data. And there's the risk of prompt injection, where a document tries to hijack the model's instructions. These are the key security risks we have to keep in mind. When teams dive into Retrieval-Augmented Generation, they often stumble on a few common mistakes. Sometimes, they ship RAG without a solid test set to catch regressions, which means issues slip through. Other times, they never evaluate how well retrieval actually works, or skip re-ranking and relevance checks, trusting everything blindly. Chunk size is another trap: too big, and the answer gets buried; too small, and you lose context. And switching providers without re-embedding causes mismatched models. These pitfalls can quietly undermine your results. Let's dive into how Retrieval-Augmented Generation, or RAG, works in a real-world Java setting. This isn't just about clever prompts, it's a series of engineering and judgment calls. Imagine a 2-second service-level agreement. Every step in the pipeline has to be timed and tightly controlled. We blend keyword and vector search to catch exact matches and close ones. Metadata filters and access controls keep data secure and relevant. Docs update daily, so we use incremental re-embedding instead of rebuilding everything. This is how a large SaaS company powers a support bot that answers questions across tens of thousands of documents, all in under 2 seconds. Now, let's dive into some of the tough questions you're likely to face about Retrieval-Augmented Generation, or RAG, in Java. We'll cover everything from preventing data leaks between tenants to evaluating if your system actually works. We'll explore why ingestion and querying need the same embedding model, keeping your VectorStore up to date, handling irrelevant retrievals, and how RAG differs from fine-tuning. These follow-up questions are crucial. They show you really understand the technology and its challenges. Now, let's dive into Retrieval-Augmented Generation, or RAG, in Java. We're building a Spring Boot endpoint that takes a question, embeds it, and then retrieves the top 3 relevant document chunks from a VectorStore. Next, it crafts a prompt with this context, calls the ChatClient, and returns both the answer and the source IDs. This slide lays out the method signature, the key components on the class path, and the step-by-step checklist to guide our implementation. Let's get hands-on and try it out. Now that we've covered the basics of retrieval-augmented generation in Java, it's time to take things further. This assignment challenges us to enhance our solution with some key upgrades, like converting the Ask endpoint into a streaming server-sent event setup, building a mini evaluation set with golden queue and A pairs, and adding a re-ranking step to improve result quality. We'll also scope retrieval by user or team, respecting access boundaries, and include metadata filtering. Share your work with at SRWebTech. The best solutions get featured in a follow-up video. That wraps up our overview of Retrieval-Augmented Generation, or RAG, and how it fits into Spring AI. Remember, it's not just about the final answer. We need to evaluate retrieval quality carefully. Security starts with controlling access to retrieved content. Spring AI's tools make this seamless in your code. Next, we'll dive into Spring AI and LLM integration fundamentals.